story.
Thank you. So before to start, I just wish to say a few words about the material needed for further reading. So for the first lecture, I talked about geometry of free manifolds. There is a beautiful paper by Peter Scott in Bulletin, London Math Society, something like 87, which describes everything with a lot of detail. And this paper is still actual. It's the main reference for geometry of free manifold. Now for the second part, I did start things about TQFT, but in a very rough way, and I start discussing mapping class group. There is a standard reference by now is Benson Farm and Dan Margaret. The book called A Primer on Mapping Class Groups. You can find it on internet. Okay. Now, yeah, I was probably not very clear and for what theorem I stated due to Caligari, Friedman, Water, which says that universal pairing is positive. So I just add what means positive for me. So you have a pairing that means a bilinear map from one vector space. I denoted it by script wj, and now this universal pairing was taking values in something which is defined as follows: is a vector space generated. You want to have a set. So if you take the collection of all free manifolds, closed free manifolds, it might be a bit too large for the point of view of set theory. So you take the set of homeomorphic classes of closed free manifolds. So it's closed free manifolds up to homeomorphic. And this makes a set. You take the free module generated by this. So it's a huge thing. Okay, and the idea is that Wj is almost the same kind of definition, but instead of closed free manifolds, you have compact free manifolds with one boundary component, and this boundary component has a natural marking into the standard surface of GNT. And this bilinear pairing comes from gluing together. So here is one generator of Wj of this form. So the boundary is a sigma j, and here is another sigma j, and you just glue them together using the marking.
Oriented free manifolds.
Oriented free manifolds. All free manifolds I have here are oriented. Actually, this has a linear form because you say that changing orientation is the same thing as conjugacy. Yeah. Okay, so what means positive? Positive is very simple. V equals 0 implies V equals 0. this is positive. This statement is highly non-trivial. After a lot of trivialities I described before, this is a very deep theorem, and it takes about 80 pages to get a proof. I don't want to say more about the proof. The idea is to have a kind of Cauchy-Schwarz inequality for free manifolds for some complexity function. We define a complexity function for free manifolds such that the complexity when you do gluing A union B should be smaller or equal than the maximum complexity of gluing AA or BB will be quality only if A equals B. This is the perfect analog of it. And once you define this complexity by means of hierarchy and so on, you could be able to prove this.
This is much stronger than Schwarz inequality.
Right. No, it's weaker.
No. The inequality itself is stronger. This Schwarz you would have the sum.
Yeah, but you divide by 2.
That's too difficult for me.
Should we vote? It's divided by 2. Yeah. Anyway, the meaning of such a theorem is that topological quantum field theories, which are quotients of such universal pairings, should be able to detect everything, meaning classify free manifolds. This is not exactly saying that topological quantum field theories based on finite dimensional representation or finite dimensional topological quantum field theory should classify. These are different statements. And actually what we could prove is that finite dimensional topological quantum field theories do not suffice to classify free manifolds. No, this is just to have an idea about how the things are. Don't hesitate to interrupt me and to ask me questions that sometimes are very vague about all this stuff. So I define what I did last lecture was to define the mapping class group, to state a theorem by Nielsen saying that the mapping class group is basically the same thing. You could define it purely algebraically in terms of outer automorphic groups of pi1 of surfaces. So the mapping class group of a closed surface of genus G is the positive automorphic of pi1 C. And of course there is a version for manifold with boundary or for manifold with typically, let me state it because it is so nice, the break groups. The break groups could be obtained in the same way using just the disk with punctures. But you have an additional. Here I put pi1 of sigma j, and it's a bit tricky, that notation, because in order to find the fundamental group, you have to pick up one base point. And this base point really does matter. Change the base point, get isomorphic groups, but yeah, it's kind of a different group, just isomorphic to it. And in this case, when you have boundary, you are allowed to take homeomorphism which fix the boundary, and you can pick up your base point on the boundary. So this is a very useful trick in mapping class groups. And now you could find that the Bn, instead of automorphic, you could go into real automorphism. So let's say this phi of the automorphism, which also preserve orientation in some sense, but this is not that clear now what would be preserving orientation. So now the fundamental group should be the fundamental group of the puncture disk. So here you have F1n. This is the free group. And now phi of some loops corresponding to one generator like that. Phi of sigma I, as I'm putting up here, this loop is conjugate to sigma I. Equivalence means conjugate. And this is a way to see the matrix. Well, a well-known way, but now my plan was to say things about generating multi-class group. So generators and their relations. Generators of mapping classes in general. So take gamma, a curve, a simple closed curve. Gamma in the surface, then you could find a regular neighborhood of it, which is a cylinder. Okay, and gamma is still contained in the surface. There is no problem of one-sidedness and so on because the surfaces are orientable. And now you could define, if this is your cylinder, you could define a transformation called left then 2 the following way. If you want to cut first by some red stuff, and you take the curve in the middle, the green curve, and now you want to twist by 2 pi one of the, in fact, the middle circle. So let me see what you're going to find if you never saw this picture. That this is going to come this way and it arrives on the same endpoint. So you want to have this homeomorphism to be trivial on the boundary, meaning identity on the boundaries, and you twist it once in the counterclockwise direction. The green part is gamma, and the red part is just one curve which enables us to see the annulus as being obtained from a rectangular piece of paper by gluing once here. Now the gluing has completely changed. Okay, so this is the left hand. There is a right hand, which is the opposite. So this is the left hand. Then twist along gamma. One of the main characters of people seeking for generators and relations in mapping class groups. Okay, now T gamma, which was defined from n gamma into itself, it is identity on the boundary, so it has an extension by identity map on sigma minus n gamma. And I'm calling and keeping it calling T gamma from sigma to sigma. And now, at the beginning it was like a homeomorphism, but now I'm taking just its class in the mapping class group. So I'm still calling it Dentwich, but this time we should think about as the class of T gamma into the mapping class group and Tg of sigma. Okay, this is uniquely defined. This is an easy exercise. What I draw here determines uniquely the class. If you could move a little bit around this curve, nevertheless, if you keep it in the same isotopic class, nothing will change. If you do that, nothing changes. Okay, observations or remarks, easy remarks. So gamma is homotopic or isotopic. I said it's the same thing. Or gamma prime implies T gamma equals T gamma prime. Now I'm seeing them in the mapping class group. If phi is a homeomorphism of gamma, of sigma, preserving orientation, then T of phi of gamma is a conjugate, phi, T, gamma, phi, inverse. So once you have a curve, by conjugating Dentwich, you could obtain many other curves, basically almost all of them.
And T gamma can be trivial, right?
Yeah. Gamma, T gamma equals 1 if and only if gamma bound a disk, namely is null homotopic. Otherwise it is non-zero. It has a non-trivial action, for instance, on pi 1. You could describe it like you do here. Yeah. Now you could see that the mapping class group of an annulus is S1 cross 0, 1. Well, actually it has nothing else than a dentist, so it equals Z, and this Z is generated by one dentist. It is this one, around the middle curve. Dentist around the middle. I have also this phenomenon saying that if you have two curves, alpha, beta, such that alpha intersection beta is empty, but to the joint curve, of course, alpha is empty, then the dentist commute. I have a lot of dentries which commute. For instance, you take a Pans decomposition of the surface, and you take the dentist corresponding to this Pans decomposition in the dentist along curve coming from the Pans decomposition. If the curve, if the surface is closed of genus G, you will find 3G minus 3 such curves, and pairwise commuting. Let me do a picture. Here is typically one Pans decomposition alpha 1, alpha 2, alpha 3G minus 3. Then you get the group generated by the dentist alpha E is giving you a map from 3 G minus 3 inside the mapping class between G and G. An exercise a little bit more interesting is the case where you have two curves alpha and beta intersecting into one point. Basically, the situation is like that. You have one curve alpha and the green curve beta. So alpha intersection beta equals 1, or the geometric intersection is 1. Now you have exercise, you have the following relation: T alpha T beta T alpha equals T beta T alpha T beta. Are called the bridge relations. Okay, so let me state some theorems. Wow, I have some place here. I'm stating that in a historical perspective. So the first results are coming from Max Den, saying that the mapping class group actually is generated by T gamma, where gamma is running over all simple closed curves, SCC. This is Max Den in the 20s. Now, I don't remember who did this, but very probably Dan was aware of that in the 40s. Is that if I'm taking G, at least 2, and also the number of boundary components can be P arbitrary, putting inside brackets, then finitely many non-separating gamma do suffice. Now you recall that you have two kinds of curves. In fact, a little bit more, but let me do the picture here. You have curves which separate, like this one. Separate. Because it separates, if you cut along this curve, you separate into two disjoint pieces. And you have curves which do not separate. This is not separating. The name telling exactly what it does. It doesn't separate if you cut along it. Now, very easy remark which is extremely useful in mapping class group. Remark number 7 is that two non-separating curves. Two non-separating curves alpha and beta can be obtained one from the other by means of an element of the mapping class group. Given there exists some phi I'm tempted to write phi belongs to the mapping class group, but actually the mapping class group do not act on the curve, do not act on the surface. This is a very old problem. Does the mapping class group? So it would be completely wrong if I write phi belongs to the mapping class group and phi of alpha equals phi of beta. But anyway, I'm writing phi belongs to the homeomorphic group sigma j, like that phi of alpha equals beta. Then you need how do you find such things? It's very easy. You cut the surface along this path. You cut the surface along the two curves, along the curve alpha, around the curve beta. What do you get? You get another surface of g minus 1 with two boundary components. By the classification theorem of surfaces, two surfaces like that should be homeomorphic. And now just pick up a homeomorphic between the two surfaces and then do the gluing back. It's very easy to see that this homeomorphic between surfaces with boundary induces a homeomorphic between the closed surfaces. In some sense, all curves which are not separating are looking alike from the point of view of homeomorphism. Okay? So the meaning of this relation is that, as I said before, somewhere here, number 2 means that T of beta is a conjugate, phi T of alpha, phi inverse. So all these dentries are conjugate. Now I'm using another notation. Phi is now a mapping class. So let me just state for those. So I said that the mapping class group is a quotient of homeomorph of sigma g into the mapping class group. Sigma, which is by definition homeo plus sigma j divided by homeo 0 sigma g, meaning those isotopic to identity. So it was a long-standing question to find whether you have here a section, meaning a morphism from the mapping class group to the group of homomorphic on the surface. And this is a group morphism. So this is section, meaning group morphism. The answer was considered first by Morita in the case where the homeomorphic groups were replaced by diffeomorphic groups. Because doing that with diffeomorphism of any class, meaning 0, 1 up to infinity, it will give you the same group here, the same quotient group. And Morita was the first to prove that there is no section. Now, section. This was proved by Morita for diffeomorphic groups. And much recently by Markovic for homeomorphism. The two proofs are rather different. Morita was using characteristic classes, and you see if you have such a section here, you take the cohomology here and the cohomology here, and it should be a splitting of the cohomology classes. Yeah.
What are the years of the result? Is it better?
What are the
date?
The date. Morita is in the 80s. Markovic is in 2000, around. So it always makes sense to say that you have elements of the mapping class group acting on isotopic classes and so on, but it doesn't make sense to say that an element of mapping class group is really acting on the surfaces and on curves. This is a side remark.
So what's the status if you just wish to lift the relation under 6? So you have two intersecting curves.
Yeah.
You wish to lift this relation in the mapping class group to geometric gain. Not whole group, just this relation.
You ask me if there is a morphism from the braid group to the homeomorphic group.
Not from the whole group, just for
one relation. One relation.
For this, for two curves, alpha and beta.
One relation I think you can get. Yeah.
You can get this?
Yeah, I think. There is a, from this point of view, there is also another very deep theorem. It's Kirchhoff theorem, saying that finite groups, which are in the mapping class, we can lift.
But this is not finite.
This is not finite, but it's a Z. Well,
no.
It's not exactly Z, but
no, much. There are two. I wish to lift both T alpha and
T beta. Yeah. I think you can lift. The problem is when you have many more. I'm not sure you can lift all of them, but B3 you can lift. This is B3. Bn I'm not sure you can lift in general. B3 I'm sure you can lift. If you couldn't lift B3, there would be a very easy proof.
Yeah, I know. But in the other way it does not work.
Yeah. No, but philosophically,
But you do not have a reference.
No, but yeah, I think you might do it by hand. I just put here the name of Kirchhoff. Kirchhoff, yes, for finite subjects. And this is an important theorem. Okay, we spent enough time for this side remark. Now the next point is the theorems by Licorice first, and this was completely improved, that's said by Gervais later, that you have the following set of generators. Licorice and then Gervais. Sylvain Gervais. So let me do a picture. I'm having B boundary components. I have continuous G. We need to pick up some curves. From symplectic viewpoint, curves are always denoted instead of alpha 1 up to alpha something. They are called alpha I and beta I. So here is alpha 1, here is beta 1, and we continue the same way. Alpha 2 is here, beta 2 is here. And you keep going up to beta G, you have G O. And we have some extra curves, so I'm taking an extra color. Delta 1, delta 2, up to delta something. We have B boundary components, here it should be B minus 1. Okay, so while I will put some more curves. So what is the theorem of licorice? Is that the bend twist along alpha 1, beta 1, alpha g, beta g, and now there is a problem if b equals 1 or not. You see, I have to add one more up here, delta b. This delta b makes sense also when the number of boundary components is 0. So here is g at least 2, p equals 0, and if g equals at least 2, p bigger or equal to 1, you have alpha 1 up to beta 1, alpha g, beta g, delta 1 up to delta b. I want to say generate. Of sigma genus G B boundary component. So from some point of view, from algebraic viewpoint, the number of generators is not that huge. They are very explicit, you can see them and you can try to work with them. It is well known by Humphreys that you cannot get, let me take the closed case, you cannot get less than 2g plus 1 density with generator. This is the minimum number. Nevertheless, people interested in group theory were always looking to groups which are two generated. If I well remember, all finite simple groups are generated by two elements. And there are many elements. There are many groups which are having just two generators. They are simple. But you can find a lot of examples of extremely interesting groups which are generating by only two elements. Now it's a theorem due to Weinrib. About 98 or something like that in topology, saying that you could generate mapping class group by two elements. To be sure, I'm taking G at least 2 and close to make it simpler. Is generated by one then twist like that by two elements. One of them is a dent twist, the other one cannot be a dent twist. By what I said. Two elements. One is a dent twist.
What is the analyzation?
Yeah, I'm gonna say in 5 minutes. It is very easy. Now let me just add some more information about let's look first at this curve. They are all non-separated. So this fits well with the case of I put here in proposition number 2. Okay? There are finitely many, of course, and they are all non-separated. let's look at the case. So I'm in the case 4. G equals 1. P equals 0. This is something you already saw here above. This is the torus. So it's SL to Z. And you have two curves. And you already saw yesterday the presentation of the group. The group is generated by these two. Now you could have P equals 1. So you do the same, but here you have a hole. This mapping class group is SL to Z. The other one is a group which is so this is M11. If you look at the center of B3, the center of B3 is generated by this dentist here. And B3 divided by the center is SL2Z again. And this is a very interesting phenomenon. If I'm taking instead of boundary component, if you take the puncture here, what you get is exactly the B3 divided by this dentist around this curve here. And this is again isomorphic to SL2. So these two surfaces have the same mapping class. And of course they are generated by curves which are non-separated. Now P at least 2, G equals 1. There is only one interesting remark to be done there. Non-separating curves are not enough. Non-separating curves are not enough to generate this mapping class group, the mapping class group of the surface of genus 1 and P boundary component. Okay. Now I will say things about relations, and having relations you will be able to compute immediately the abelianization.
Suppose you take a Dean twist along a separating curve. How do you express it in terms of Dean twist or non-separating one? Easy to say.
Yeah, I don't have an algorithm, but if you give me the curves, I think I should be able to write it down.
Okay. So how about take a genus like a 4, take the middle separating curve?
Yeah, in general, it's rather easy if you have a curve like that. If you have a curve like that, you just use the product of all this. You take the product in order, and you will find this curve.
The power of that product is the dentist.
Right.
Dean twist in the middle.
Power.
The power, right.
No, Dean twist in the middle, not in the.
Yeah, but
Oh, okay.
you assume you cut here.
Yeah.
So the middle becomes like this kind of curve.
Yeah. So what's the expression?
You have to do alpha 1, beta 1, up to alpha p, g, p, beta p, and then look at the power. I think it's pi minus 1 or something like that.
If there's only alpha and beta, then it is 3.
Are you sure? there is that kind of relation, but the way to prove it, yeah, let's say put 3, and this is delta. In order to prove that, you have to see how this is acting on curves.
But it is the monotony of a singularity, so therefore you know it.
Yeah, if you know many things, you are able to do it, yeah. Right. There are some interesting presentations due to Matsumoto, which are saying that the mapping class group, at least when you have a boundary, one boundary component, is like an arting group. Is almost an arting group of this kind. And you have to pick up all, and this is related to the singularity theory. But the way to see is just to identify this action on curves. You see how it looks on a point decomposition. If the action is trivial on curves, then that means that by Alexander's theorem, this has to be an identity in the mapping class. But yeah, it is not something, it is not a clear algorithm. You could give a hint of how to compute such things. Okay, so let me go to relations. I said already I have some nice relations on the point 6 here. I'm just recording them again in the form of the, so here I'm the point of relations. So here are the braid relations. In the braid case, you have two types of relations. Those which are commutativity, so I'm putting T alpha, T beta equals T beta, T alpha, if alpha intersection beta is empty, and I'm having T alpha, T beta, T alpha equals T beta, T alpha, T beta, if alpha intersection beta equals 1. These are braid relations. And in many cases, however, you have two intersection points, and that makes things more complicated. The typical and probably the most important relation is the so-called long-term relation. In this long-term relation, here alpha and beta, if alpha and beta are disjoint, that corresponds to an annulus. If alpha and beta crosses each other in one point, that the neighborhood of this type is a one-pole torus. Now, Laurentien relations are supported on a curve, on a surface which is a sphere with four poles. And now I have to call somewhat the boundary components. Let's say alpha 1, alpha 2, alpha 3, and alpha 4. So this one. Now I have some extra curves I'm gonna write in red. The curve which surrounds alpha 1 and alpha 2 will be called beta 1, 2. The curve which surrounds alpha 1 and alpha 3 will be called beta 1, 3. And here there is a beta 2, 3. The way I'm writing the left-hand product does not depend on any specific order, because alpha 1, alpha 2, alpha 3, alpha 4 are disjoint or pairwise commuting. The way I'm writing the right side will depend greatly on how I write it, so I have to be a little bit more careful. So I'm T beta 1, 2, T beta 1, 3, T beta 2, 3. The interesting part of this relation is that you have on the left side 4 elements, on the right side 3 elements. Is the first relation which is not homogeneous. And this has a lot of implications, of course. There is one more interesting relation I'm gonna put here called star relation, which arises in more when you enter more deeply into the structure of mapping class group, but not for the usual way to work. So now the surface is the following one. So you have here one curve and call it beta. Here you have gamma 1, gamma 2, gamma 3. And here you have alpha 1, alpha 1, alpha 2, and alpha 3. So this star relation in the following way: T alpha 1, T alpha 2, T alpha 3, T beta, and now again you have to put a power equals T gamma 1, T gamma 2, T gamma 3. So the power is 3 again. I think it's the same 3. Yeah. Yeah, there is a typical, there is one more relation one often uses when gamma 3 is trivial. And you see if gamma 3 is trivial, you just cut it out of there. Now, one of the important result in the presentation due to Sylvain Gervais, but he's closing a number of work on mapping class group presentation done by Hatcher and Thurston, who were the first to prove that this is a finitely presented, then by Weinlieb, who gave a presentation which has meant to exist, but is not that interesting. Then the one by Makoto Matsumoto, which is the most sympathetic and most easy to recall. But this one by Gervais is extremely symmetric and extremely useful in practice, at least from my point of view. Is that here you need to add some more curves here between the I and J. I'm adding a curve like that. I'm calling gamma AG. Okay. And what he's saying, Gervais, is that alpha 1, beta 1, alpha j, beta j, g, delta 1, delta b, and then gamma rg. Generate mapping class group with and give a presentation. By means of braids, lantern, stars among them. So I am considering those relations which could be obtained from the curve alpha e, delta, and gamma, and these are giving you a number of relations, and these relations are sufficient to find the group presentation. Okay. From here you see immediately that for G at least 3 you could put inside a genus G surface one lantern. Now you could also see that if you have only curves which are non-separating, I told you that two non-separated curves are conjugate. So their image in H1 is the same. Conjugate element projects onto the same. So here you have the same element 4 times, here the same element 3 times. So that means the element is trivial. It is a corollary due to initially by...
Excuse me, you are already on -5.
Okay, I stopped here. So the idea was that H1 of mg equals 0 for G at least 3. Yeah. Sorry.
Thank you. Are there any questions?
Well, so this presentation is quite involved, but there's a possibility that mg is possibly a non-normal subgroup of some simple group. Do you know if anybody considered such a possibility?
Simple means in algebraic sense or simple
The usual
philosophical sense?
daily sense, yes. Some
Here I
difference
know
between
if it's a linear.
What's your question? If there is a
If the mapping class could be realized as a subgroup of some nice and with a better presentation.
mixed representation, it's
With a better presentation. It's a subgroup of a group. I'm not sure.
by the way, in your statement is among others. So besides these 3 relations, you have some other relation, right?
Among them,
Yeah.
Yeah, by means
you take all the relations between the alpha I and beta I and delta and so on, which can be seen as grades and so on.
okay, so these 3 relations are enough.
Yeah.
Any other questions? No? Then let's thank the speaker. We have a break until 10:30. Next talk starts at 10:30.
So the vanishing of this one follows from this